Alrighty, let's continue jumping to the glorious third dimension of degeneracy pressure study. So we said we made the cubical star approximation, right, so to speak. So we've got a particle in a box, particles in a box. We're going to fill it with electrons, magical electrons that don't interact with one another, but are still fermions, so that they do obey the Pauli exclusion principle. So our box is L by L by L on the side. That's our star. Our constant density, really, we're just going to get expression for degeneracy pressure and how it depends on density, and it'll work. It'll be fine. So, as we said last time, psi is a product. There's a normalization constant, which is not really going to be too important to us, times sine of n sub x pi x over L, sine of n sub y pi y over L, times sine of n sub z pi z over L. So it's a product of three one-dimensional infinite square well wave functions. A 1D infinite square well energy eigenfunction, to be fancy here, because there's no claim that an electron's wave function has to be this. In general, it's going to be a superposition, but we can treat it as the electrons are occupying the states of well-defined energy. These are the states of well-defined energy, and the energy is just the sum of the three 1D infinite square well energies. And again, I'll have you joyfully show all this. We're just going to take it for granted here. It's just the sum. And so E, and we could subscript it, nx, ny, and z, and this could be psi sub nx, ny, and z. In other words, we're labeling the states with the values of nx, ny, and nz. Just like in one dimension, we could say like psi sub 6 and E sub 6, the energy corresponding to n equals 6. Well, there's three n's now, n sub x, n sub y, n sub z. And that's what these are, Kathleen. N sub x, n sub y, n sub z is what those are. So we're labeling the wave functions with the three n values. And the energy is just the sum of what you would have gotten for each of the individual infinite square well wave functions. So remember, it was h bar squared over 2m times, right? Remember, for the 1D, it was En was h bar squared k sub n squared over 2m, and that turns into n squared pi squared h bar squared over 2m L squared. When you put in that k sub n is n pi over L. What is it? N pi over L. So here we just got to add the three of them together, and so it'll be nx squared plus ny squared plus nz squared over 2m L, I think it was L, yeah, 2L squared times pi squared h bar squared. And I better double check that I have that right there. Yeah, okay. All right, what questions do you have at this point? Right, so I'm just adding the energies that I would associate with each of the n's, and there's an nx and an ny and an nz, so I've got nx squared pi squared h bar squared over 2ml squared plus ny squared pi squared h bar squared over 2ml. Add all three of them together, I'm going to just do nx squared plus ny squared plus nz squared. Yes, question?
So x, y, z are the spatial coordinates.
The spatial dimensions, yes. I'm sorry?
What are the ends?
The ends are the number of half wavelengths that fit along each dimension of the box. So the wave function is a product of three one-dimensional infinite square well wave functions, right? So for the one-dimensional infinite square well, if I was just looking along the x direction, here's x equals 0, x equals L. If n was equal to 2, what would the wave function look like if you sketched it? Two humps, yeah, two humps, right? Yeah, because an integer, n is the number of half wavelengths that fit inside the well. So this would be the n equals 2 version, right? Well, what I'm saying here with our cubical box is it's a product, so you have to, the real wave function of x, y, and z, you got to multiply the three of them together. Now, I could not plot that because if I have a function of x, y, and z, if I wanted to make a plot of that, I'd have to have another axis perpendicular to all three of those. And I can do that in 4 dimensions, but I don't live in 4 dimensions. But we can make like contour plots or color them in or so forth. If it's a 2-dimensional box, then you can actually sketch. You can actually draw the wave function as a function of, say, x and y. You could make a plot like that, and it would be a product of sinusoids in the different directions. So you'd have like, it would look like a square membrane, if you will, where it was wiggling up in some directions and wiggling down in other directions. It would be sinusoids in each direction. And so I could have that here in the x direction, n sub x is 2. And then, okay, in the y direction, here's y equals 0, and here's y equals L. And if ny is equal to 3, why, what do I plot there? 3 humps, yeah. 1, 2, oops, I can't count. 1, 2, 3. So that would be the ny equals 3. And I don't know, what do you want n sub z to be? What is it?
5.
Jerk. Okay, 5. Okay, why, how many humps do I have to draw, jerk? Yeah, 5. Let's see how I do. Jerk. Okay, let's see. Did I do it? 1, 2, 3, 4, 5. Yeah, kind of like that. Yes, right? And so this would be a product of those 3 wave functions, right? So if this is like the x-axis and this is the, well, let's see, let's let this be the, yeah, z-axis and how fancy can I get here? Oh God, let's see, I have to think about this. Right, and here's the y-axis sticking in there, right? Then what I've drawn over there is, ooh, there's 1 wiggle along the x direction and 3 wiggles along the y direction. And I'll let you draw the 5 wiggles along oh sorry, that was the y, that was the z direction. 3 wiggles along the y direction inside the box. 1, 2, 3. Okay, I'll try. Maybe, okay, anyway. Damn, okay, so multiply those 3 functions together, and that's the wave function inside the box, is the idea, right? Okay, yeah, that's the idea. And notice that, let's see, if you are along, say, any wall of the box, like if you're in the xy plane, what is z equal to, what is z equal to in the xy plane? Everywhere in the xy plane, z is 0. What is the wave function equal to when z is equal to 0? 0, because the sign of 0 is 0, right? And then, okay, what if I am on the surface z equals L? In other words, I'm parallel to the xy plane, but I'm on the top face of the box where z is equal to L, right? Well, if I put in z is equal to L, I get sine of nz times pi. What's the sine of nz times pi? Also 0, right? Because sine of anything times pi is 0. And you can make the same argument for all of the faces of the box. And so the wave function vanishes on the walls of our container, which is what led to the wave function being, just like in one dimension, infinite square well, integer number of half wavelengths fitting inside the box. In other words, what we have here is what we could call vanish on the walls BCs. Psi is 0 on every wall of the box because it's supposed to be that the potential energy is infinity outside the box, so the particle can't get outside of the box. So just like in the one-dimensional infinite square well, the wave function is 0 on either end. Here it's 0 on every surface of the box. On every face of that box, the wave function is equal to 0. This does the trick. That product of wave functions does the trick because all of these wave functions vanish at x equals 0 and x equals L, y equals 0 and y equals L, z equals 0 and z equals L. They're all 0 at those values. Does that make sense? That's the idea here. Okay, so now I should I should turn on the projector here so that I can show you this nice slide that I want to show you, because it's a lot easier for me to project the slide than it is for me to draw it. And I also remember I gave you the slides. I hope you have them with you here. So I should have turned this on beforehand, but I didn't. Oh well. Wish you had a good professor. Oh well, too bad. I'm going to exceed my vision right now. Whoa, that was scary. All right, and get this up here, and all right. What I want you to picture is we're actually ultimately going to be in K-space. Yes. Kathleen space, as some of us humbly like to think of it. Have you talked about K-space in StatMech yet? I bet you will. Okay. But you'll have heard it here first, and you'll be like, oh, trivial. Come on, Dr. Tree, stop boring us. We already know this. All right, so every allowable wave function that satisfies the boundary conditions and has a definite energy is of that form, right? It's some normalization constant times the product of three one-dimensional infinite square well wave functions that vanishes on the walls. And so what we can do is imagine constructing n space, if you will. So in other words, we've got a space where points in it represent the values of n sub x, n sub y, and n sub z. Now, if we pretended that those could be any number, then you could live anywhere inside n space. But we know that nx, n sub x, n sub y, and n sub z actually have to be not just any real number, they have to be Could n sub x be 2.7? Nope. They have to be like 1, 2, 3. If only there was a name for numbers that are called like 1, 2, 3 integers. Yeah, they have to be positive integers. Now again, really, that's a choice. We could insist they're always negative integers, or n sub x and n sub y are positive and n sub z is negative, because of this idea that if you made n sub x go to minus n sub x, you would just multiply the wave function by -1, but when you took the square, that wouldn't change the probability. So we can make the choice that n sub x, n sub y, and n sub z are always positive. Can any of them be 0? I mean, they could, but what would be wrong with a wave function if I made one of those equal to 0? It would just be 0 everywhere, and why don't we like the wave function being 0 everywhere? There's no particle there if the wave function is 0 everywhere. So n sub x, n sub y, and n sub z have to live in the positive octant of three-dimensional n space, right? In 2 dimensions, we talk about the 4 quadrants, right? In other words, in 2 dimensions, if here's like x, that's an x, x, y, quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? But in, right, 4 quadrants, right? What quadrant am I in? All that kind of business, right? Both coordinates are greater than 0, y is greater than 0, but x is less than 0. Both coordinates are less than 0, x is greater than 0, y is less than 0. In 3 dimensions, you have 8 octants instead of 4 quadrants, right? And we are in the positive octant, the one octant of 3-dimensional space where all of the coordinates take on positive values. And all the other octants, at least one coordinate is taking on negative values. So what we can do is we can say every possible energy eigenstate can be identified with a point in n space whose coordinates are n sub x, n sub y, and n sub z. And we can think of a vector whose components are n sub x, n sub y, and n sub z that connects the origin to one of these dots in n space. It's a cubical grid of dots in n space that represent the points where n sub x, n sub y, and n sub z are all positive integers. Questions, comments, observations, because this is absolutely crucial to understand this point, to visualize what we're doing here. So we're going to live in n space where every dot, like this one right here, is identifiable with the wave function that has those 3 values, n sub x, n sub y, and sub z. They're the components of that point in n space. Okay? Having said that, I could choose to work in n space, but in honor of Kathleen, we're going to work in k space instead. Yes, we're going to work in k space instead. And here is, not that, here is, where'd it go? Here is the 2-dimensional version of k space. Imagine I was only in 2 dimensions, so I've only got x and y. Leave off the z for a minute. If I'm in 2 dimensions, and you'll get to practice this in a homework problem, if I'm in 2 dimensions, then the wave function would just be of x and y, and it would be just this term and this term, but we'd leave off the z term. There'd be no z direction term. Oh, every time I touch this thing. Stop it. Okay. All right. So remember that we said that k in the 1-dimensional version, we said k sub n was n times pi over L, because we said psi is equal to a sine kx, which was a sine n pi x over L, So we're defining k to be n times pi over L. K is n times pi over L. And just to be sure, and you know, this kind of thing, think about this when you're not in class, right? This kind of stuff that you want to reason this all out in your head. You know, repetition is the key to learning. The 7,400th time you hear something, it finally sticks, right? So how is k related to the wavelength of the sinusoid? K is
2 pi over lambda.
2 pi over lambda. K is 2 pi over lambda, right? So the wavelengths of the sinusoids are related to these k values by the wavelength is 2 pi over k, and k is, the wave number is 2 pi over lambda. I'll pause for you to write things down should you care to. What might I decide to call what might I decide to call nx pi over L? In one dimension, I just said k is n pi over L. I'm in 3 dimensions now, so maybe I should still call things k's, but maybe subscript them. So what might I call n sub x times pi over L? Why, that could be called k sub x, yeah. So we'll call this k sub x, and we'll call that k sub y, and we'll call this, no, we're going to call this Jim. No, we're going to call it k sub z. K sub z, yes, right? So we're going to think of our wave function as being psi of x, y, z is equal to a sine of k sub x times x, sine of k sub y times y, sine of k sub z times z. And you know, I'm doing this thing where it's, you just understand that this is not the sine of all this stuff together, right? In other words, if you like, you can put parentheses around the arguments, but often you don't, because you just understand that everything that's next to a sine function that isn't starting something else, like another sine function, is the argument of that sine function. But if you want, you can put parentheses around there to keep it nicer for you.
Just asked you this question, but I forget.
Uh-huh.
What's n again?
So n sub x, well, yeah, so like for the one-dimensional one?
No.
Or just, yeah. So right here, it's the number of half wavelengths that fit along the x direction is n sub x. And it takes on values of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right, just any positive integer. And similarly, n sub y can be interpreted as the number of half wavelengths that fit in the y direction. N sub z is the number of half wavelengths that fit in the z direction. You can think of it that way. And on the whole, they code for the energy, because the energy is n x squared plus n y squared plus n z squared over 2ml squared times pi squared h bar squared, right? And while we're not going to stay in n space, because we like Kathleen too much to stay in n space, right? I could say that this is n squared pi squared h bar squared over 2ml squared, where by definition now n squared is n x squared plus n y squared plus n z squared, oh God, plus n z squared, right? So then it looks just like the one-dimensional version, except n squared is now the sum of the squares of the 3 n values. And if we go back into n space temporarily go back into n space here, notice that n squared is the square of the length of this vector right here, right? This dot itself would be, if I take n dot, this vector n, whose components are nx, ny, and z, if I dot it with itself, I get the square of its length, because every vector, whether or not it has self-respect, its square, its dot product with itself is the square of its length. So, in other words, if I draw a vector from the origin to one of these points in k-space that maps onto one of the allowable wave functions that has definite energy, then the length of that vector is n, where n squared is nx squared plus ny squared plus nz squared. And so if you think about it, that means that this is really nice thing that the energy of the state is how far that state is from the origin in n space squared multiplied by pi squared h bar squared over 2ml squared. And furthermore, all the states that were on the surface of a sphere would have exactly the same energy. And that's going to be super crucial too. Because what we're going to end up doing is saying, okay, well really the states are discrete like this, but if there's gazillions of particles, then the amount of n space we fill is so large that we can just pretend that there's this density of points in n space. We'll get to k space. Density of points in n space, and we can find how many points are in a spherical shell in n space, actually it'd be k space, and so on and so forth. And it's just gorgeous. It's just so pretty. And what's your question?
So for a star, if we are to determine energies of a particle which is far away from the center of the star,
Go ahead.
Sorry, it would have more energy automatically given.
So we have to be really careful here, right? So you have to think here, n space is an abstract mathematical space. It's not physical space. Physical space is meters from the origin, right? All that sort of thing. Do not, I forbid you, do not think of this as the center of the star, and that this is different positions within the star. This is a separate space. It's not physical spatial space. It's an abstract mathematical space. And so anywhere within, so we would think of like in our cubable box here, the problem we're really solving here, every electron is spread throughout the whole box, right? Because this wave function is spread throughout the whole box. There's just places where the wave function is large, the particle is more likely to be found. Where the wave function is small, the particle is less likely to be found. But it's just this spread out wave function that fills the entire box. So you can't say that the particle is close to the origin or far from the origin or anything like that within the space of the box. It's just got a probability density. This is a mathematical space that we used to talk about what particles are in what wave functions and so forth, as you'll see as we go along. So this has nothing to do with the physical space of the star. Don't think of it that way. By the way, don't think of it that way. Yeah. Okay. All right. What other questions do you have? You look like you're about to ask a question. Yes.
So
Yeah.
n determines the length of the vector and n squared determines the energy.
So I would say that nx, ny, and nz are the coordinates of the vector. And so the vector which has those coordinates, the energy is the length squared of that vector times all this other stuff. Okay? Now, having said all that, we're going to instead think in terms of k-space. So in other words, rather than nx, ny, nz, we're going to go into k-space and talk about k sub x, k sub y, and k sub z. And if we want to, So what do we know about k sub x, k sub y, and k sub z? Can k sub x have any possible value whatsoever? Is it allowed to just take on any value whatsoever? It is not, because k sub x can only take on values of an integer, a positive integer, times pi over L. It's not allowed to have any other values. So just like n space, you're only allowed to be on points within n space, not any arbitrary point, but the points on that like cubical grid. Same deal in k space. So just to make it easier to draw, we've got the two-dimensional version here, k sub x, k sub y. You can't be along the axes. Why can't I not be on the x-axis, on the kx axis or the ky axis? Why can't I be at this point right here where k sub x is equal to 0? K sub y is equal to 0. Why can't I be at this point right here in k space? There won't be a particle, right? Because if k sub y is equal to 0, the wave function goes away. The wave function goes away. So I am only allowed to be on one of the grid points in the positive quadrant. In 3 dimensions, it'll be a grid point in the positive octant. But in 2 dimensions, I have to be at one of these grid points in the positive octant. Because k sub x has to be an integer times pi over L, and k sub y has to be an integer times pi over L. So I have to be at one of these grid points. So I could be at pi over L comma pi over L, or 2 pi over L comma pi over L, or 3 pi over L comma pi over L, and so on and so forth. What are the coordinates of this point right here? What is k sub x for this point right here? What's k sub x? So what's k sub x for this point right here? Pi over L, right? In other words, k sub x for this point, well, okay, let me put it this. What is n for this point? And sorry, what is n sub x for this point right here? 1. What is n sub x for this point right here? 2, 5, etc. So, in other words, n space and k space, they're similar in that to get k space, you have to multiply everything by pi over L, if you like. Okay, so this is k sub x equals pi over L. What about this one? 2 pi over L, 4 pi over L, etc. K sub y right here is 3 pi over L, etc. Right? What about this point right here? K sub x is and k sub y is 3 pi over L, right? So the coordinates are integers times pi over L. Integers times pi over L, right? So, right? Kx, ky, and kz are all integers times pi over L. Integers times pi over L. Those are the allowed points. So if I were better at drawing in 3 dimensions, why, I could draw something that looked like this, except that here this would be like pi over L, 2 pi over L, 3 pi over L, 4 pi over L, etc. Everything would have a pi over L attached to it. It would still be a grid, okay? And here's a super crucial concept. So I will draw a bit of that grid there because it turns out I do have the competence needed to draw a grid in 2 dimensions. Maybe you could draw a 3-dimensional grid. I can't. I mean, I could, but I would be here for an hour with me trying to make it work, okay? So k sub x, k sub y. All right, and I'll just be like, so this would be, so if you want to have some fun later, play back the video, and you know how you can make YouTube play back faster and it does some digital processing so that the voice still sounds the same? If you play this back fast later, it's going to sound like I'm a woodpecker. It's going to be like, right? Very entertaining. Right, here's just play it back fast. Because what we're about to develop is the idea of the K space volume per state, and turn that into the number of states per unit volume of K space, which will be absolutely crucial to everything we do. And I'm really confident you're going to see that again in StatMech/thermal physics. And again, you're going to be like, oh, we have this so down. Sit down, Dr. Trees. We'll just handle the lecture from here. It's going to be glorious. All right. Maybe I didn't have to draw all those points, but I started getting just like, well, I'm here, right? So pi over L, 2 pi over L, 3 pi over L, 4 pi over L, pi over L, 2 pi over L. And by the way, if you could also make it a rectangular box, and then you'd have LX, LY, and LZs. They'd be like unevenly spaced, but then you're just like, it just make it slightly harder for no good reason. 4 pi over L, dot, dot, dot. All right. What we want to do is say, okay, I'm going to say that I draw that. It should be a square. I didn't draw everything. It should be a square. But every state kind of has its own personal volume of K space that you can kind of say it gets, so to speak. It owns. In other words, if you drew a bunch of squares centered on each dot, which can represent one of the allowable energy eigenstates, why, you would completely fill the space. And let's see, how wide is one of these squares? So we'll go whoop, whoop. Right? So here's one of these squares there, and I drew this box around it. How wide is each side of that box? Well, it's as wide as the distance between the states, because each box goes halfway over to the next state. So how far apart are the states from one another in each direction? Pi over L, right? So this is pi over L, pi over L. And so here in 2 dimensions, we would say that each state owns, if you will, quote unquote, a K-space area of pi over L times pi over L equals pi squared over L squared. So the K-space area per state is equal to pi squared over L squared. But wait a minute. If we had been doing the 2-dimensional problem we would have said, okay, instead of the one-dimensional infinite square well, I'll have the two-dimensional infinite square well, where I've got the particle confined to a box that is of length L in each of the x and y directions. So the particles inside a box of length L, or our particles are inside a box of length L. What's the area of that box? L squared, right? Area of container, area of the box is L squared. So in other words, we can also say that this is pi squared over the area A, capital A there, of the box. It's the area that the particle is confined to. Pi squared over A. The K space area per state is pi squared over A. So, the number of states per unit area in K space is, well, if the K space area per state is pi squared over A, what is the number of states per unit area? Right? This is area per state, and I mean K space area, which has different units from physical space area. So if pi squared over the area of the box, pi squared over L squared, is the area per state, what's the states per unit area in K space? What do you do? What's that? Yeah, so says, yeah, more specific, yours, yeah. Yeah, okay. So let's do, suppose we were a bunch of people standing around in this room, okay? And I say, so suppose we all had everybody standing on a grid in this room. And when all was said and done, we would say, why, every person has their own personal area equal to 2 square meters. So that means that the number, that the area per person is 2 square meters. How many people are there per square meter if each person occupies 2 square meters? What do you do? 1 half, right. What'd you do to get 1/2 out of that?
I took people in there and divided by,
Yeah, you took the reciprocal, right? You flipped it over, right? If there is 1 person per 2 square meters, right? I'm sorry, I meant to say, if there's 2 square meters per person, right, then, okay, now I've got to get myself here. Okay, if there's 2 square meters per person, then there are half a person per square meter, right? You flip it over to go the other direction, right? Okay, same deal. If there's pi squared, I'll leave the A out for a moment to avoid confusion. If pi squared over L squared is the K space area per state, what do I do to that to get the density of states in K space is what it's called, the number of states per unit area in K space. You do it right, you flip it over. It'll be L squared over pi squared. L squared over pi squared. Or in other words, A over pi squared. Stop it, pi squared. I'm thinking ahead there to 3 dimensions. A over pi squared. Number of states per unit area in K space is A over pi squared. This is called the density of states. And it shows up for sure in thermal physics And it is an absolute staple of solid-state physics. It's everywhere in solid-state physics. The density of states is the number of states per unit, really in 3 dimensions, volume of K-space. In this 2-dimensional example, it's states per unit area of K-space. Yes. Oh God, thank you for pointing that out. Yes. Right. Okay. Yes. That is, oh man. That is so fundamental. Ah. Yeah. Okay. Ay, ay, ay. There we go. Look at that glorious grid right there that you weren't getting to see, people at home. I'm crying now. Ah. Okay. I should, if I were really fancy, I would edit this video and put that video, take a snip out and put that video so they could see it before I started blathering on about it. Hey, yeah, okay. I'll have to put a note in there like, okay, before you watch timestamp this to that, go to timestamp that, stare at it for a while, and then listen to the rest of it, something like that. Yeah, or even fancier. My wife does video editing. You can actually, I could actually put this there and then put an audio track under it, right? Then I got to think about how to do that. But what's that? Yeah, it's not too hard to do that, right? Yeah. Okay. Yeah, actually, what I think I'm going to do is I'll take a photograph that can then be the frame that just sits there for a long time and has a soundtrack under it. Let's see, but I better make this the right dimensions there, which I don't typically switch. So let's see, I gotta get, where's the settings for this? Well, I can always crop it later too, but I'll just crop it later. Okay. Doink. Okay. So how are we going to modify this for 3 dimensions? In 3 dimensions, we would have a third direction here, and so now each state occupies a volume, if you will, in K-space instead of an area. So in other words, it'll be like these cubes here, except center them on red dots, and they have length on here. It would just be their side is 1. But in K-space, it's still pi over L in every direction is how far apart the states are in all 3 directions. So in 3 dimensions, each state is associated with, it owns it, whatever you want to call it, with a volume. And I can actually kind of draw this here. So I'll just draw one of those cubes in K-space. So there's my dot in the middle. There's the cube of K-space that it sort of owns, it occupies. How long is each side of that cube? What's that? Pi over L, right. Just the 3-dimensional version of this. Add a third dimension. Pi over L. Pi over L. Pi over L. Pi over L. It occupies a volume of, what's the volume of that cube? Pi cubed over L cubed, right. Pi cubed over L cubed. but wait a minute, our original box that the particle is actually in physical space, you have to keep reminding yourself, K space is not physical space. The particle itself is in a box, or the particles themselves are in a box of side L. So what is L cubed in terms of that box right there? That is the volume of that box. So we can say this is pi cubed, and I'm going to kind of write it like that to be clear that that's a capital V right there, where V is the volume of the container, volume of the box, the container, the volume of the container. So the density of states in K space is what? What do we call the density of states in K space? The volume per state is pi cubed over capital V, the K space volume per state. So the density of states is, yeah, volume over pi cubed. The volume of the box divided by pi cubed. That's the density of states in K space. The reason we're going to use that is we're going to say next, after we take a break, that in the ground state, every particle gets as low an energy as it can manage, but you can only put 2 particles in each state because of the Fermi exclusion, Pauli exclusion principle. And so you end up filling up an octant, a spherical octant, a sphere in an octant of a sphere in K space, because the energy is proportional to n squared. It's also proportional to k squared, because k, the coordinates in k are just pi over L times the coordinates in n. And so every state within a spherical surface has less energy than on that spherical surface itself, because how far you are from the origin in k space is directly related to the energy of the state. So we'll go through that next time, or next time is after, the next period, right, after the break. And that'll allow us to find the Fermi energy and an expression for the degeneracy pressure and all this wonderful stuff. So much to look forward to. Yes?
What tells of a low energy state and a high energy state in an octane?
So let's just wait until wait till the next period, right? And I'll be going through all that. And if you're still confused, ask me again. Yep. Yeah, yes indeed. So, shall we continue? Something to point out here that maybe you were puzzling about, maybe you didn't notice, is that we said that the K space volume per state is pi cubed over the volume of the box. But wait a minute, I said that volume has units of 1 over volume, but it does because, so what are the units of K? Right? What are units of K? Well, K is an integer times pi over L. What's the units of pi? Dimensionless. What's the units of L? Meters, right? So what are the units of K? They're the same as the units of pi over L. 1 over meters. K has units of reciprocal meters. You can also get that from the fact that it's sine kx times x, right? Sine ky times y, the argument of a sine function has to be dimensionless. So kl has to be dimensionless. L has length units, so k has to have reciprocal length units. So in other words, k space volume has units of meters to the minus 3. reciprocal meters cubed. K space volume has units that are the reciprocal of physical space volume. So it's perfectly fine that the K space volume is pi cubed over the physical space volume of the box. K space volume has units of meters to the minus 3. If I put in the units, it would be meters to the minus 3 for the units of that. The K space volume is in reciprocal meters cubed. And furthermore, the density of states, right, has units of meters cubed. Well, density we normally think of as, right, per unit volume, but K space volume has meters to the minus 3 as its units. So per unit volume of K space has meters cubed as its units. K space has the reciprocal of the units of physical space. So that's an aside to explain how that can be. How that can be. And again, remember that K space is an abstract space. It's a mathematical abstract space. It's not physical space. And so we're using this abstract K space to be able to say things about our system, essentially. Keep that in mind. Just like N space, it's not physical space, it's an abstract mathematical space. Now, I'll say some stuff that maybe won't make that much sense to you, but I just want to plant a seed here, which is that in quantum mechanics, in fact, you know, we always talk about typically the wave function as a function of x, y, and z. That's in coordinate space. But you can also write a wave function in momentum space. You can write a wave function that's a function of p sub x, p sub y, and p sub z. And the momentum space wave function absolute squared times dpx, dpy, dpz is the probability that the particle's momentum will be in a little volume of momentum space, as opposed to finding the particle in some little volume of physical space, of coordinate space. And not only that, the physical space wave function and the momentum space wave function are Fourier transforms of one another. And it's a property of Fourier transforms that if the function of x, y, and z is spread out, the function, its Fourier transform is narrow and vice versa, and that's where the uncertainty principle comes from. It's because the momentum space wave function and the physical space wave functions are Fourier transforms, and when one is broad, mathematically it's automatically true that the other one is narrow, and that's why if you know the particle's position better, you know less about the momentum, because if you know the particle's position well, its physical space wave function is concentrated, but it's automatically true that its Fourier transform, the momentum space wave function, will then be spread out so that you, quote unquote, don't know as much about how fast it's moving, what its momentum is. And I love that, and I'd love to just start teaching about that, but we can't. We got to keep going with this stuff. But I'm just throwing that out there because, oh my God, it's so freaking cool. And the day that I comprehended that was like one of the biggest days of my intellectual physics life, because like, oh my God, I understand the uncertainty principle. I was just like blown away. So maybe you too can look forward to that point where you're like, that's the uncertainty principle. Oh my God, right? Dr. TR's husband is an engineer, and he knows about Fourier transforms. One day I'm having a conversation with him at Huntington Park, where the Columbus Clippers play, because we were at one of these SSRP game nights, okay? And he's talking about the uncertainty principle, and I said, you're an engineer, right? You know about Fourier transforms. So I told him that the position and momentum space wave functions are Fourier transforms, told him there's also a position space wave function, and his reaction was like, right? Same thing. It's like, oh my God. That's I get it now, right? I could just see the light bulb going off. It was glorious. All right. So I want that light bulb to go off for you someday. Maybe a little bit went off right now. I don't know. But at least maybe a dim flicker started, if not the whole flash bulb. But let's keep going with this, okay? So the number of states per unit volume of K-space is pi cubed over the volume of the box, pi cubed over L cubed, all right? What can we do with this? Or sorry, each state's associated with that. So the density of states is what I meant to say. Number of states per unit volume is in K space is L cubed over pi cubed, or the volume of the box over pi cubed is the density of states in K space, the number of states per unit volume of K space. So here's the idea. Here's the big idea. Remember last time I said, okay, for the one-dimensional infinite square well, we could say, all right, and I drew these, energy levels and all that, and I said, okay, let's start putting particles in there. Where's the first particle go? N equals 1. Where's the second particle go? N equals 2, because I'm trying to minimize the energy. I'm making the T equals 0 ground state minimum energy conversion. Where's the next one go? Yeah, and then the next one, and then the next one, and then the next one, etc. I could just as well have said, well, in one dimension, we've only got K sub x, or N sub x, if you will. And so in one dimension, all we've got is, here's the different K values for the particle, that a particle can have. So here's pi over L, 2 pi over L, 3 pi over L, etc. Okay, so I just make dots along the kx axis, because for a one-dimensional particle, there's only the kx axis of K space. All right, and here's the origin 0. I put in the first particle. Which dot represents the state of the first particle that I put into the box if I put it in the lowest state available to it? The first one, right. So I put in the first particle right there. The first particle goes in. It's in the ground state, the single particle ground state. Where do I put the second particle? Same place. It's also in the ground state. Where do I put the third particle? The next one, right? There goes the third one. I can even be fancy. I'll make the little arrows that are the spins, right? So first particle might be spin up, and then the next one has to be spin down, right? That whole business. So if I keep putting in particles, they just keep occupying the dots, if you will. But the energy of each particle, for each particle, E is equal to what in terms of K, right? In other words, E was equal to h bar squared something over 2m. What's the something? What's that? Not even that. Yeah, just K squared. H bar squared. In one dimension, E is h bar squared K squared over 2m. H bar K is like the momentum, P squared over 2m, because it's only got kinetic energy. H bar squared K squared over 2m is the energy. So in other words, the energies are directly related to how far I am from the origin of K space. And it's the square of how far I am from the origin of K space that determines the energy. You have to multiply by h bar squared over 2m, but the square of how far I am from the origin determines the energy. You look puzzled. So E is h bar squared K squared over 2m, right? Oh, yeah, you didn't see me when I said that. I don't have to do that. I'm just saying, oh yeah, remember one spin up, the other spin down. So I'm just sort of kind of saying, oh, spin up particle, spin down particle, spin up particle, spin down particle. Because remember, the Pauli exclusion principle says you can only fit 2 particles in a given state and they have to have opposite spins. So I'm just kind of qualitatively saying the first particle goes into this state, the second particle goes in there too, and they have opposite spins.
Each dot on the K select is
is a state. Yes, it represents a state. That's the point.
It has 2 particles.
And it has and it can have as many as 2 particles in it. And in the ground state, the next particle in, if we're constructing the ground state, always goes into the lowest available state. Which state has the lowest available energy? So the first 2 can go in here, the second 2 can go in here, the third 2 can go in here, and so forth. Now, if I heat the particles, then they'll start occupying other states. That's what reflects the fact that it's no longer a T equals 0. But at 0 Kelvin, you're in the minimum possible energy, and so you do this business. If these were bosons instead of fermions, they would all crowd into the ground state, because bosons can do that. But fermions cannot. They have to go to higher and higher states because the Pauli exclusion principle says, no, only 2 particles per state, no. And so they're like, okay, I guess I'll go sit up high from the field, right? Okay. Now, in 3 dimensions, in 2 as well, but let's go ahead and kick it up to 3 dimensions. Kx, ky, kz. Let's say here's one of those allowed states. So there's my vector k. My vector k is k sub x, x hat. I like to use x hat, y hat, z hat as the unit vectors instead of I, j, k, because x hat kind of says, hi, I'm a unit vector in the x direction. You can use I, j, k if you like, and you often do that, but are you okay with me using x hat, y hat, z hat as my unit vectors? K, y, y hat plus k, z, k sub z, z hat. So I define the vector k to be kx x hat plus ky y hat plus kz z hat. The energy is h bar squared k squared. Well, if I write the whole thing out, right? Well, this would be, what's k sub x equal to? It's something, it's an integer times what? Pi over L. And what do we call the integer in the x direction? N sub x. So this is n sub x pi over L x hat plus n sub y pi over L y hat plus n sub z pi over L z hat. The energy is nx squared plus ny squared plus nz squared pi squared h bar pi squared h bar squared over 2m L squared. If we're in n space, that's what we said the energies were. But how can I write this in terms of kx, ky, and kz? What is nx squared pi squared over L squared? What is nx squared pi squared over L squared? That's k sub x squared. And similarly for y and similarly for z. So we can also write this as kx squared plus ky squared plus kz squared times h bar squared over 2m. The energy is h bar squared times kx squared plus ky squared plus kz squared over 2m. Don't you just love Kathleen space? Yeah.
Oh, I have a question.
Yes.
Why is it called K-space?
Why is it called K-space?
Why
Why is momentum P? I think it's the same answer. Yeah. Yeah.
Not that I completely.
Right, but yeah, that's, I don't know where it got to be K. Yeah. Somewhere along the way, somebody decided it should be K. And that's K. That's okay. Right? Yeah. Uh-huh, yeah. Okay. K dot K, what would I write for K dot K if it's KXX hat plus KYY hat plus KZZ hat? What's K dot K? It is, but what, in terms of its components, right? A vector dot itself in terms of its components is kx squared plus ky squared plus kz squared, right? The dot product of a vector with itself is always the sum of the squares of its components. So k dot k is kx squared plus ky squared plus kz squared. And like usual, we usually just call k dot k like that. We just say that's k squared without the arrow on it, saying like, in other words, that's just the magnitude of k squared. So with that understanding, the energy is just h bar squared k squared over 2m, like before. H bar squared k squared over 2m, but now k squared is the square of the length of the vector in k space that is pointing to the little dot that maps onto our wave function, that maps onto our energy eigenfunction. So remember that when we're in k space, all the dots can be mapped onto the eigenfunction a sine kxx, sine kyy, sine kkz, sine kzz. The dots represent eigenfunctions, represent allowed states that a particle can have such that it has a definite energy. In general, a particle's wave function can be a superposition of states. But let's keep it simple and just say the particle is in an eigenstate. Right? So this is part of the beauty of k-space, is if k is the vector that represents the particle state, its energy is h bar squared k squared over 2m. H bar squared over 2m times how far you are from the origin in k space squared is the energy. Distance from the origin squared in k space is directly proportional to the energy of the particle that has the state in question. So, if you look at, and again, this is n space, but k space means just multiply everything by pi over L. All the coordinates are multiplied by pi over L. I don't have a picture of that, but just mentally multiply every coordinate by pi over L. This is the origin of what I say. So in other words, any two states that are the same distance from the origin have exactly the same energy. Do you remember, what do you call it? It starts with a D. If two states in quantum mechanics have exactly the same energy, those two states are, they're degenerate, yeah. They're degenerate. So, I guess I'll zoom out here so the audience at home can kind of see everything there more so, right? So, if two states have the same energy, they're degenerate. Any states on the surface of a sphere in k space are degenerate. They have exactly the same energy. because they're exactly the same distance from the origin. So this pink sphere, it's really a surface of a sphere, it's really an octant of a sphere because we're living in the positive octant. Life in the positive octant. It's so positive, right? Yeah. Ooh, I'm in the positive. It's so good in the cup. Stop it. Anyway, everybody on that surface, all those states have exactly the same energy. Now, they're dots, right? So it's not too likely that a dot's going to be exactly on that surface, but any dots that were on that surface would have exactly the same energy. And if you think of, okay, what if there's gazillions of zillions of particles, huge number of particles, so we're occupying many, many states. In that case, these dots would be so close together that you can kind of think of them as like a continuous fluid of dots. And you can say, okay, everything on this surface has the same energy. And so the idea will be, okay, now what if we were constructing the ground state? Where would I put the first particle? Which state has the lowest possible energy amongst all these? Well, let's go back into 2 dimensions where it's easier to draw the picture. Every particle has to live on one of these grid points. Which one of these states has the lowest energy? Make my finger stop when I hit the state with the lowest energy.
Stop.
Yeah, because of all the states available, that's the one that is closest to the origin, right? Because the energy is entirely determined by how far you are from the origin. So that is the lowest energy state. So the first particle in the box goes into that state right there, which will be one hump in both directions, right? Because the ground state is the one hump state, right? In 3 dimensions, it would be one hump in all 3 dimensions, right? So it'd be like 1/2 wavelength fits along all 3 directions. Yes?
Like, what's the difference then between,
This one and this one?
yeah,
They have exactly the same energy. They do. So where's the second particle go?
Same spot.
Same spot. Where's the third particle go? Take your pick. It could go in either one of these states. We don't care. It could go in either one. And then the fourth one, well, it could go in either one. And then the 5th one could go in either one. And the 6th one could go in either one. But the next one can't because we've put all 4 particles in there because each one can hold 2. So the next one will have to go to the next closest state to the origin, which would be this one right here, right? So there will be some ambiguities, right? When you have degenerate states, there will be some degenerate states along the way. But in general, you'll keep filling up. Each time you drop a particle into the closest state to the origin that can still hold a particle, which could be ambiguous. There could be some states that are tied for that honor. That's all right. That just means you've got more possibilities for here, like for the next 4 particles, well, they just have to go into these 2 states. And it might be first this one and then this. You drop the particle and you say, pick the best seat. It's like, again, it's like this seating situation, right? Where sit as close as you want, right? Well, it might be there's one seat that's closest to the field and somebody sits there, and the next person might be, well, these 2 seats are equally good. Just pick one, flip a coin and pick one, right? So your particles are flipping coins, deciding which one to be in. Okay? And so let's suppose we put in a bunch of particles into the box, and they're all inside this semicircle, or this circle here, right? This quadrant of a circle. They're all inside that circle, right? So what have we done? If I put, those are all the states that are closer to the origin than that circle is, right? They're all closer to the origin. All the ones that are inside the circle are closer to the origin than the circle is. So that would be the ground state for however many particles would fit in this set of states. So how many particles would fit in this set of states? What would I do? How many states are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, blah, blah. There's a certain number of states. How many particles could fit in there? That times 2, because each state can hold 2 particles with opposite spins. So for that many particles, that would be the ground state of the system. And h bar squared, that distance k squared over 2m would be what we call the Fermi energy. That would be the energy of the highest energy occupied states at temperature 0, at 0 Kelvin, where you've created the lowest possible configuration you can in terms of energy. So the radius of that circle is what we call k sub f, the Fermi radius in k space, and h bar squared k Fermi squared over 2m is the Fermi energy, we call that. So for our plot there, that's radius k sub f, the Fermi radius, in k space, and the energy corresponding to the k values on that circle, h bar squared k Fermi squared over 2m, is the Fermi energy. After, of course, Enrico Fermi, famous Italian physicist. EF is the energy of the highest occupied states at T equals 0 Kelvin, because at T equals 0 Kelvin, you've minimized the energy. You get to where you could not extract any further energy out of those particles. They're at their minimum possible energy configuration. You just can't make it any smaller. Because all the seats are occupied. Yes?
So does the fact that we're like denoting it just that it's in k space mean that there's a Fermi radius?
No, it didn't. No, there is no Fermi radius in configuration space, or I mean in physical space. No, I'm just emphasizing that it is a radius in k space, not in XYZ space. Yes. So notice for a given box that the Fermi energy depends on how many particles you put into the box. As I keep adding particles, what happens to the Fermi radius? It keeps getting bigger, because if I added more particles, I'd start occupying states out here. So the Fermi energy and the Fermi radius depend on how many particles are in the box. And we'll see that explicitly. And so, well, we'll see that explicitly. We'll get to that. Yes, question?
I know this is not a physical workspace, but if the temperature increases, then that means that there's more particle diffusion happening. And
So for a given number of particles, that's a very good question. For a given number of particles, I've got a certain number of particles in the box, and I'm going to heat the box and see what happens. Heat it up and see what happens. What happens is particles start occupying states that are outside the Fermi radius. Okay? And the idea is that you could calculate this energy, And you would say, so in a classical thermodynamical system, you expect a typical particle energy to be roughly kT, where this K is the Boltzmann constant, right? There's not enough symbols to go around, geez, right? So the Boltzmann constant times the temperature is the typical particle energy, right? At T equals 0 Kelvin, what is the Boltzmann constant times T? It's 0, right? So in classical thermodynamics, at T equals 0 Kelvin, all the particles would just be motionless and they would have 0 energy. There's this difference between quantum physics and classical physics. According to classical physics, at T equals 0, there's no energy in the system. They're just all sitting there at rest. But the exclusion, the uncertainty principle and the exclusion principle together, they won't allow that. So even at T equals 0, the particles can have significant energies if you've put a lot of them in there. Even at 0 Kelvin, they could have lots and lots of energy moving around, if you will, quite quickly. So we drop these particles in the box, we figure out what the Fermi energy is, okay? What do you think happens if the temperature I heat it to is such that the Boltzmann constant times the temperature is way larger than the Fermi energy? That means a typical particle's thermal energy is way bigger than the Fermi energy. So where does that particle live in K-space? Is it still inside here, or is it way out here somewhere? It's way out there somewhere. If Boltzmann constant times the temperature is way out here somewhere, then what has happened when you heat it up is the particles migrate and fill up lots and lots of K-space, and then the gas or the system behaves pretty much classically, you can show. It acts like a classical ideal gas in that limit. But as I cool the system down, the particles start in K-space, right? It's an abstract space. They're not physically moving anywhere. You cool them down, they're slowing down, if you will, but that corresponds to smaller K values in K-space. So you cool it down, and they start migrating back towards the origin. And if it's such that the thermal energy is well below the Fermi energy, but not 0, then there'll be a few particles out here, but most of them will still be inside the so-called Fermi sphere, or in this case, the Fermi disk in 2 dimensions. And that means that, yeah, there's a few particles out here, but the classical thermal energy, if it's much less than the Fermi energy, the classical thermal energy's in here somewhere, not that large. So classically, you would expect the particles to have these kinds of energies, if you will. But quantum mechanically, there's lots of them out here that have nearly the Fermi energy. So in other words, the particles are, if you will, much more energetic because of quantum mechanics than they would be if they could be treated classically, such that the Pauli exclusion principle didn't force them up into high energies, because only 2 particles get to occupy any given state. And that's when we've got degeneracy pressure. When the thermal energy, Boltzmann constant times the temperature, is small compared to the Fermi energy, then most of the particles have energies that are much larger than you would expect classically, because classically you would expect some energy much less than the Fermi energy, but quantum mechanically, there's lots of particles that have energies near the Fermi energy. Because if you think about it, there's a lot more area out here than there is close to the origin. So most of the particles will have energies that are pretty close to the Fermi energy. They're zipping around at energies way larger than Boltzmann constant times the temperature. And so they exert much more pressure than they would as an ideal gas would, where the typical energy would just be Boltzmann constant times the temperature. And the reason why degeneracy pressure doesn't depend on temperature very much, it's actually a lie, it depends a little bit on it, is that as long as the temperature is well below the Fermi temperature. The Fermi temperature is where the Boltzmann constant times the temperature is equal to the Fermi energy. As long as the actual temperature is well below the Fermi temperature, heating it up just promotes a, see, because, okay, let's suppose all these particles, most of the particles are inside the Fermi sphere. Suppose they're mostly inside the Fermi sphere. There's a few of them out here. I heat it up. Let's say all these states are occupied right here. I heat it up. Can this particle jump over to this state if it's already occupied with two particles? No. If any states that are already occupied with two particles, a particle in a nearby state in K-space can't get into it. Those seats are already taken. The only particles that can change their energies are the ones that are close to the Fermi surface. So you heat it up, and a few particles migrate a little bit outside the Fermi surface, but you've hardly changed the overall typical energy of the particles because most of them had nearly the Fermi energy anyway. So when you heat a degenerate gas, you only slightly increase the pressure because a few particles wander outside, a little further outside the Fermi surface, but their energy was already almost the Fermi energy, and now it's the Fermi energy pressed a little bit more, and so that hardly changes the pressure at all. So when we've got the helium flash, the gas is degenerate. And so, okay, it's not 0 Kelvin, they're not all inside the Fermi surface, but they're mostly inside the Fermi surface. You start to heat it, and a few of them wander outside the Fermi surface and exert a little extra pressure because they got a little bit more energy than they had before, but their energy before was mostly due to quantum mechanics, the Pauli exclusion principle. Now I give them a little bit more. So is it really true that the pressure doesn't rise at all? No, but it rises just a teeny little bit. You might as well ignore it. And so it gets hotter, and the reactions go faster. It gets hotter, reactions go faster, until the temperature gets so high that the temperature exceeds the Fermi temperature. And that's the point where you're starting to get lots of particles out here. But you got to get to like well over 1 billion Kelvin in that degenerate core for that to happen. When you get to a high enough temperature, you get enough particles outside the Fermi surface because Boltzmann constant temperature becomes larger than the Fermi energy. Then you get to the regime where it acts like an ideal gas, because one can show if most of the particles live out here, well outside the Fermi surface, in that limit it behaves like a classical ideal gas. And so we lift the degeneracy and the helium flash is over at that point. Yeah, nah, right? Yeah, we go from helium flash, to no more helium flash, nah, right? So to speak, right? Yep. Okay. So, yeah, so we'll get started on the next piece of this then. All right. So we've said also. So what questions do you have at this point? And there's a lot, right? I'm like, are you thirsty for knowledge? I have a fire hose. Please enjoy. Right? Yes.
Could you say that, like, outside of that radius, they behave more like towards the classical side?
No, I wouldn't put it that way. It's a collective behavior. So if most of the particles are inside the Fermi radius, it's a degenerate gas. If most of them are outside the Fermi radius, it's more. It's in that limit. It becomes more and more like a classical gas, right? So the classical ideal gas doesn't exist, but it's a limit that quantum mechanics approaches for a gas of fermions when the actual temperature is much larger than the Fermi temperature, which is the same thing as saying that the K-space states occupied by a majority of the particles lie well beyond the Fermi surface in K-space. Their energies are much larger than the Fermi energy. Okay? So let's show how to get an expression for the Fermi energy. How do we find it? All right?
What are fermions, Dr. Manning?
Fermions are particles that have half integer spins, right? So electrons, protons, etc. Helium-4 nuclei are bosons. They have integer spin. Photons are bosons. And the spin statistics theorem from quantum field theory proves that fermions obey the Pauli exclusion principle. That if you have two spin 1/2 fermions, only two of them can occupy a given spatial wave function, eigenstate, and they have to have opposite spins. So fermions, spin 1/2 particles are the most typical examples, are particles that have to obey the Pauli exclusion principle. Bosons don't. So if you have a bunch of helium together and you cool it a lot, it all crowds down into the ground state. And then you get things like, it can flow without viscosity. Why? Because viscosity is a type of friction which starts to change some of the motional energy of the fluid into random thermal energy. But if everything's in the ground state, you can't extract energy anymore, and as a result, you get superfluid. You can't have viscosity because you can't extract energy if everybody's down in the ground state. It's already in the lowest energy in that situation. So all the at T equals 0, all the helium atoms go into the ground state. Whereas with fermions, only 2 can go into the ground state. With bosons, it's a party! They can all go into the ground state. That's not a restriction anymore. They can all sit on the closest seat to the field and like, cool, we love one another. Oh, this is great. We're all in this seat. Oh, this is right. Whereas fermions are like, get off of me, right? So bosons are more, yeah, they're chill. They're gregarious, right? I joke with my wife. I have this theory that says cars are bosons. Because when I park in the parking lot, trying to not have anybody park next to me, I walk out and I'm like, I'm way over there and 2 cars are parked next to me. So cars are bosons because they tend to congregate. Yeah, which is annoying to me. But anyway, okay, so here, okay, I'm going to finish with like, oh, this is going to be great next time. But I just want you to see the basic idea here today. Here we are, kx, ky, kz space. I'm going to draw the surface of a sphere in the positive octant. And this sphere is the Fermi surface, which has radius k Fermi. The Fermi surface is like that circle over there, but in 3 dimensions. It's the surface of a sphere instead of the edge of a circle. The Fermi surface has radius equal to the Fermi radius. To find k sub f, so in the ground state, right? In the ground state, all the particles are inside here, right? In K space, they're all inside here. They all have energies less than the Fermi energy, just like over there in the ground state. So ground state, all particles are in states that lie inside the Fermi surface. Because you have to be careful, because we get sloppy and we say all the particles lie inside the Fermi surface, but it's an abstract space, so the particles aren't literally inside of it. We'll just say that sloppy. What we really mean is they are in states, the vectors that represent, they're in states such that the vectors in K space that represent them all lie inside the Fermi surface would be the long way to put this. All particles are in states that lie inside the Fermi surface because we're minimizing the energy. The minimum energy will be where you've crowded them all into that sphere, and occupied every state within that sphere such that there's no more room, just like over there. That's the ground state. To find KF, we multiply, here's the cute part here, we multiply the volume enclosed by the Fermi surface we multiply the volume enclosed by the Fermi surface by, ooh, here it comes, the number of states per unit volume in K space. By the number of states per unit volume in K space. The number of states per unit volume of K space. Because if there's a huge number of states inside here, well, then we could get an awfully good approximation to the number of states in there by saying, okay, what's the area of this quadrant circle here, this circle? Well, what's the area of a whole circle with radius k sub f? That area would be pi k Fermi squared, but it's only one quadrant, so it's just a fourth of k Fermi squared. If I took, in this one, a fourth of k Fermi squared and divided that by, and I multiplied that by the number of states per unit area, right, which was L squared over pi squared, that would give me an awfully good approximation to how many dots are inside there. It's like saying, you know, think of these as floor tiles, right? Think of these as floor tiles. If I knew the area of that semicircle and I knew how big each floor tile was, I could give you a good estimate of how many floor tiles are in there. It's actually rather like counting how many pixels are inside an aperture in aperture photometry, as a matter of fact. So you look like you're not quite happy with that.
I'm struggling to wrap my head around a lot of it, but I think it's just going to take some...
This is one of those, yeah, doing some outside thinking here, right? So each of these squares has area pi squared over L squared, right? So I take 1/4 pi k Fermi squared and divide that by pi squared over L squared, and that's the number of squares inside of there, to an awfully good approximation. We're missing the fact that, well, some of them are partial squares and all that. But the bigger this gets, the smaller a correction that becomes. If this was way out here and there were literally 10 to the 18th states in here, that's a tiny correction on the edges, is the point. It would be, you could definitely see the effects here of the misestimation, but when we've got an Avogadro's number or more of particles in there, that ain't gonna matter anymore. Yes?
Is it kind of like when you were doing like Riemann sums, how there was like little stuff whenever...
In a sense, it's kind of like that, yeah. It's kind of like that. This certainly, you could say, you could think of this as, it's analogous to finding the area by doing a dx dy integral and adds that up and it's equal to the area of this and then the limit blah blah blah, except we don't take the limit because we wanted to stop with pi over L, so to speak. So just, I know this is bonus time, but we just got to get to this point. We have to, okay? Let me do this. Let me do it, okay? By the volume per unit volume of K space, okay? And set that equal to the total number of particles. Okay, so this is the last thing I'm going to write. I promise. It's the last thing I'm going to write. Here we go. But it's going to be so glorious, you're going to be like, oh, my life today would have been incomplete if he hadn't continued. Now I can actually enjoy the OWU Connection Conference tomorrow. So, okay, here we go. Here's the products. 2 times 1/8 times 4/3 pi k Fermi cubed times L over pi cubed is equal to capital N, where N is the number of particles. All right? But let's take each piece of this. What is 4/3 pi k Fermi cubed? That's the volume of the sphere, except why did we also multiply by 1/8? It's only the first octant. It's only the first octant, right? So volume of the sphere, but the 1/8 is there because only the first octant. Only the first octant. So the total occupied volume of space case, that of Kathleen space, is 1/8 times 4/3 pi k Fermi cubed, right? So these two together is total occupied volume of K space. And what is L cubed over pi cubed? Or L, that's the density of states, right? This is number of states per unit volume of K space. Number of states per unit volume. So this times this will be the number of dots, the number of states that are occupied in the ground state. Yes?
Wait, so everything except the 2 is what you just said?
Everything without the 2, right? So this will be so all this together then is the number of occupied states, all that together, right? So volume times states per unit volume equals number of states, K space volume times how many states there are per unit volume, right? This is analogous to volume times particles per unit volume to get the total number of particles, that sort of thing. We're missing one more thing. Why is there a 2 there?
2 states.
2 states. Spin. Spin. Right? So this many states times 2 particles in each state is the total number of particles in the box.
Glorious.
Glorious. Glorious. So next time, it's easy to solve for K Fermi here, right? Solve this for K Fermi. Well, this was V, right? So when I take that over to this side, I'll get the number of particles divided by the volume of the box. That's the number density. That's the number of particles per unit volume. So K Fermi depends on the number density. And that means it doesn't depend independently on N and V. All it cares about is how tightly packed are my particles together. That's what's controlling everything. So what it comes down to is degeneracy pressure depends on density. It doesn't care about temperature. Ideal gas law depends on both density and temperature. But degeneracy pressure says, go away temperature. I only care about density, the number of particles per unit volume. And the point is, in a white dwarf, everything's so packed together that the density is large enough that, wow, the Fermi energy is very large, the Fermi radius is very large. There's a lot of frickin' pressure there, enough to hold up a white dwarf. Until the particles become relativistic. Oh my God, Chandrasekhar, okay, limit is when the particles become relativistic. See, if they're not relativistic, the more energy you give them, the faster they're moving and the more momentum they have. But there's a speed limit in the universe. What's the fastest the particles could possibly go? speed of light. When it becomes so dense that the Fermi energy becomes so large that the particles are becoming relativistic, you can't keep adding momentum so readily because of the fact that they're bumping up into the universal speed limit. And that's why degeneracy pressure is no longer able to support the gravity, because you keep adding mass, and so you keep increasing the energy, but the momentum's like, it's not keeping up anymore, and so the pressure is no longer able to keep up with the gravity, and you get a limit to how big your white dwarf can get. Okay, more next time. You can enjoy the Connection Conference. Yes?
Could you please write L cubed over there for picture?
Right here? You mean you want me to be like L cubed over pi cubed, so that then you can...
Bold bracket or anything's fine.
Right, okay, so... Yeah, there you go. Yes, uh-huh.
You can pause if you like you always do. Perfect.
How much would you pay? Don't answer yet, because wait, there's more. Before I forget, Anushka, would you like to help Don show people the sun tomorrow?
Yeah.
Yeah, okay, absolutely. Yes, he would like that. So yes, uh-huh.
I'll be there. What time?
I better check with him. I think it's the same time as last time, like 1:30 to 3:30 or something like that, but I'll do, yeah, uh-huh, yep. Yeah, do you have his email? I think you do. Yeah, so send him an email saying, yeah, I want to help, and then he'll get back to you. Yep, yes. And yeah, by the way, if you want to see the sun through the cool solar telescopes tomorrow, go see Don by Merrick at like in the afternoon. Yeah, like 1:30 to 3:30, something like that. In fact, you know, you're welcome to just join the party and be a helper too. So yeah, yep.